Partial derivatives. Consider the function z equals f of xy. We want to define the partial derivatives in the following way. And notice the two different notations that are used. So the partial derivative of x is the limit as h goes to 0 of f of a plus h comma b minus f of a comma b all over h. And the notations are either f with a subscript x or something that looks like df dx, but the d's sort of look like backwards sixes. Similarly, the partial derivative with respect to y is the limit as k goes to 0 of f of a comma b plus k minus f of a b all over k. Now, what's really going on here? So hopefully you recognize these definitions of the derivative, just like there were in single variable calculus, with a little bit of an exception. And let's take a look at the partial derivative with respect to x, particularly this first part, f of a plus h comma b, and then now let's look at the back part. Do you notice that the only thing being affected is the x? In fact, there, the y part, the b, if you would, remains constant. So that's really the key to understanding these partial derivatives. Give you more explanation with this picture here. So z is a surface in space. So I like to imagine it as being like a mountain or something. And imagine that you're standing at some point on the mountain, and I call that point z naught here. And you want to find the slope of the mountain at that point. Well, how can you do that? Especially considering that at any point there are potentially an infinite number of slopes, depending on the direction you look or the direction that you travel. So imagine standing at a point on a mountain and just doing a 360-degree turn and noticing that in any of those directions you might be walking at a different slope. Those, by the way, are called directional derivatives. But we're going to look at two particular directions. What if we were to walk or look parallel to the x-axis? If we are looking down the path that's parallel to the x-axis, what you would notice is that the y's don't change at all. If we're walking parallel to the x, we're at some sort of fixed y. Similarly, if we're walking or looking parallel to the y-axis, the x's don't change. Because if we're going parallel to the y, we're at a fixed x value. So when we say the slope parallel to the x, with our notation f subscript x, what does this mean? It means that the y's are held constant, or the y's are treated as a constant because they're not changing. And if we're going down something parallel to the y-axis, we want to find the slope, which we're going to call f subscript y, or the partial with respect to y. The x's don't change, which means the x's are constant. So in practice, partial derivatives are very simple to find. Let's do some examples to understand them. Consider f of xy equals 4 minus x squared minus 2y squared. And we want to find the partial, that is the partial derivative of f with respect to x. Well, this simply means that we consider or hold all y's to be constant. And we would just treat them as we would the constant rule, because they're not changing. So the partial of f with respect to x would be 0 minus 2x minus 0 again, because we just treat y as a constant. Similarly, if we're doing the partial derivative of f with respect to y, we consider or hold all x's to be constant. We treat them as constants because they're not changing. So the partial with respect to y would be 0 minus 4y. Another example. Consider f of xy equals x cubed plus x squared y to the fourth minus 3y squared. And I'm using both notations here to get you used to it. The partial of f with respect to x is 3x squared plus, now how do we handle this part? It's not a product rule. We would handle the derivative of x squared times y to the fourth in the same fashion that we would handle 8 times x squared, which is we ignore the constant and just multiply by the derivative of the x part. Well, same thing here. The derivative of x squared y to the fourth, partial with respect to x, is 2x times y to the fourth. And then the derivative of 3y squared and negative 3y squared is 0 because there are no x's in it. The partial of f with respect to y is the derivative of x cubed, but x cubed is a constant in this case, so we don't need that. And then the derivative of x squared y to the fourth is treat x squared as a constant times the derivative of the y part. And then the derivative of negative 3y squared with respect to y is negative 6y. And certainly we could rewrite this in a slightly different form, kind of a more standard form, as 4x squared y cubed minus 6y. Okay, what if we have more variables? Here, f of xyz equals xy squared minus 2y squared z cubed plus 5z. What's the partial with respect to x? Well, the partial with respect to x means all other variables are treated as constants. So the derivative of xy squared is y squared, just like the derivative of 10x would be 10. And that's it, because there are no other x's. The derivative of f with respect to y would be x times 2y minus 4y times z cubed, and then plus 0, because everything that's not y is treated as constant. And the partial of f with respect to z is, well, this first part, the derivative will be 0 because there are no z's. And the next part, we'd have negative, and then 2y squared times 3z squared. So we'd have negative 6y squared z squared, and then plus 5. Very briefly, let's look at the notation for higher order partial derivatives. The first notation, f(xx), says take the derivative with respect to x and then with respect to x again. The other notation, remember that we start inside parentheses and work our way out. So this says take the derivative of f with respect to x, and then, I'll put first, and then do it again. It doesn't really affect many things till we get to the next part. But this is usually written as partial squared of f with respect to partial of x squared. Nothing's being squared, that's just a notation. How about the partial of f xy? Well, this says we're going to do the partial with respect to x first, and then the partial with respect to y second. So the other notation is kind of backwards, but we know we start inside parentheses first. So we're saying the same thing, but it looks different. The partial of f with respect to x first, and then we do it with respect to y. And the notation would be partial squared of f over partial y partial x. And we can see these other two, so I'll go through these quickly. The partial of f with respect to y, then x. So first y, second x. We're saying the same thing over here. Y first, x second. And the notation partial squared of f over partial x partial y. And of course, partial y, you just do the partial with respect to y first, then again. Quick note, and we will take advantage of this throughout the course. If the partial of f xy and the partial of f yx are continuous on the domain, which they very often are, then f of xy is going to equal f of yx. Let's do one example of those. Consider f of xy equals x cubed plus x squared y cubed minus 2y squared. And we want to find the second order partial derivatives. That is, we want to find all four of these down here. We have to start by finding the first partials. So the partial with respect to x is 3x squared plus 2xy cubed. Convince yourself that's true. The partial with respect to y is 3x squared y squared minus 4y. Now, let's do the partial with respect to x, and then with respect to x again. So we have 6x plus 2y cubed. So I'm just taking the partial of this thing with respect to x. But now let's do the partial of that with respect to y. So with respect to x first, and then with respect to y, and we end up with 6xy squared. I'm just taking the back derivative of this back part only. How about the partial with respect to y first? So now let's do the partial with respect to y first, and then with respect to x. And notice that we get 6x y squared. And those two are equal. And now let's do the partial with respect to y first, and then with respect to y again. And this is going to give us 6x squared y minus 4. So our mixed partials, we call those the mixed partials, are equal. And we can know this because our function is continuous everywhere, so continuous on any domain. But the other partials, the other second order partials, do not have to be equal.